Okay, in this section, you guys, we're talking more applications of integrals. The goal is to calculate the hydrostatic force and hydrostatic pressure on a submerged object. What does hydro mean?
Water.
Usually has to do with water, although the fluid we're looking at doesn't necessarily have to be water. But that's what the author of our book calls it, so I'm going to stick with that. Hydrostatic force, some books would call it maybe fluid force, and hydrostatic pressure on a submerged object. So here's the basic non-calculus definition of I guess, fluid pressure or hydrostatic pressure. I'll just call it P for pressure, okay? So here's the definition. Pressure. So imagine an object like yourself submerged in a swimming pool. If you've ever been in a swimming pool or in the ocean or whatever, the deeper you go, the higher the pressure, right? So we needed to invent a definition that takes that into account, so that the deeper you are, there's more pressure on you, and you felt it on your ears if you ever dived deep in a pool of water before. So here's what the definition turns out to be. We take the weight density of the fluid. What do I mean by weight density? How much the fluid weighs per cubic unit. Okay, so that's either going to usually be in cubic meters or cubic feet. So how much the fluid weighs per cubic unit. That's what I mean by weight density. And then maybe multiply it times depth, right? Because that's going to increase that pressure then will increase the deeper you are, or the deeper the object is. So times depth. And I'll just shorten this to W times D. Now, in the last section, W stood for work. It doesn't stand for work here, right? You just have to get used to that. It stands for the weight density of the fluid. So let's see if we can work an example here based on that simple definition. Suppose a penny is lying 8 feet flat. It's lying flat on a horizontal bottom of a swimming pool, 8 feet below the surface. Find the pressure on the penny. Well, according to this definition, P equals W times D. Let's actually do the unit analysis on this one too. Usually, I don't like putting units in the middle of a calculation, unless I want to learn something about the units. Okay, but let's actually put the units in here. So we're dealing with feet, right? Which tells us that we're using English units. So the measurement your book uses for the weight density of water is 62.5 pounds per cubic foot. Okay, so let's put that down. So in for W, I'm going to plug in 62.5, and doing the unit analysis, pounds per cubic foot. So that's the W portion of the formula. And then the depth portion's easy. It's given to you right there, 8 feet. And then if you do the unit analysis, remember the units cancel just like numbers do. That's how we create our units. What are we going to have on the bottom? Square feet. So we're going to get 62.5 times 8 pounds per square foot, which should make sense to you because you want the pressure on the surface of the object submerged, right? So it should be per square unit. Okay, so what does 8 times 65 turn out to be? 62.5 rather turn out to be? Check me. I think it's 500. And then it should be pounds per square foot. So that's your pressure. Before we do the next example, I think it's worth noting that fluid pressure, what we just discovered is that fluid pressure, or just pressure, is measured in force per unit area. Last example, pounds would be the force per unit area would be the feet squared, square feet. But we're also interested in the total hydrostatic force or total force on an object. And so to get that formula, we actually multiply by the area. So if this is note number 1, then the total hydrostatic force on a submerged object well, okay, let's think about it. The formula we just got done using gives us pressure, right? So let's think about this. We know that the pressure is equal to weight density times depth, right? Well, if we multiply both sides of this equation by area, in other words, get rid of that per square foot or per whatever it turns out to be when you calculate the pressure, then that should give us the total force. So F for force is going to be pressure times area. But the formula you want to memorize is the WD times A, because all you have to do then is memorize that formula for the total force on a submerged object, and then take off the factor of A if you want the pressure on the submerged object. Does that make sense? All right, so what do we have here? In this example, we suppose that a rectangular tank is 8 meters long, 4 meters wide, and 1.5 meters high. Suppose that the tank is filled with a liquid of density 820 kilograms per cubic meter. So that's not a weight density, is it? That's the true density that you learn about in science class, mass divided by volume, right? Yeah. So we have to take that into account when we work the following problem. So that's not a weight density like the last problem, so we have to keep that in mind. In part A, we're going to find the hydrostatic, just the pressure. Look at the word that comes after a hydrostatic. We're going to find the hydrostatic pressure on the bottom of the tank. So part A, let's draw a picture of the bottom of that tank just to make sure we're on the same page. The bottom of the tank, what would the dimensions of the bottom of the tank be? 8 by 4. It's the height of the tank that's 1.5 meters. So 8 meters by 4 meters. So we want to find the pressure on the bottom of the tank, and it'll be in, per square units, right? Per unit area. Okay, we can do that. I don't think this is a calculus problem, guys. The bottom of the tank is at a constant height. You're going to find out later on that when the height of the object is not constant, then calculus may come into play. But here, the bottom of the tank is at a constant height. So I don't think we need any calculus. This is just like the penny problem from the last example. So we're looking for pressure. Hydrostatic pressure, let's just call it P for pressure. P is equal to what? W times D. What does W stand for in this case? Weight density. There may be a little more work here than in the last problem, finding the weight density. Okay. The weight density, well, we know the density. But we have to turn that 820 kilograms into a weight, and the measurements we use in this class are called newtons. How do you turn that 820 kilograms into newtons? Remember Newton's law. Force equals mass. We have mass. Kilograms is mass times acceleration, which is 9.8, right? meters per second squared. Now, I'm not going to do all the unit analysis here. I'll leave that to you guys, you budding physicists. But I will turn this into newtons by taking 820 kilograms can be turned into newtons by just multiplying by 9.8. Now, it's already per cubic meter. So this will be the weight density. Because it's 820 times 9.8, the per cubic meter didn't go anywhere. So there's your W. And then what's your depth? Well, how much of the tank is filled? Yeah, the whole thing is filled, I think, right? Yeah, it's filled with the liquid density. Okay, so it's filled is 1.5 meters high, so the depth of the bottom of the tank would be the full 1.5 meters. There's your depth. And so what units should that be in, by the way, since it's important to keep this in mind. You could do the unit analysis or just realize there's only a couple of different choices. I mean, in the last example, the units are always in force per unit area, right? So in the last example, we were in American units, so it was pound per square foot. So what would it be here? We know it's going to be in newtons, right? So before we do the calculation, newtons per square meter. And if you actually run through the unit analysis, you'll see that that's true. What did this turn out to be? Did anybody do this multiplication? 820 times 9.8 times 1.5? Okay, so 12,054 newtons per square meter. Now, there's a name for that in the metric system. Newtons per square meters called pascals. Because there was a philosopher who was also dabbled in physics. You know, people back then, they dabbled in lots of different areas, science and religion and philosophy. And his name was Pascal, I guess. Pascal, of Pascal's triangle fame, right? So it's named after him. So 12,054, they use PA for that, but it stands for pascals. Okay. Let's find, now this is different. Let's find the total hydrostatic force at the bottom of the tank. So what's the total force? What do you need? What other factor do you need besides W times D? A. So the force is W times D times A, but guess what? We've got that first multiplication, W times D, we have, right? That's 12,054. So W times D is the 12,054. We already computed that in the last example. Okay, what area are we speaking of here? The bottom of the tank. Well, how do you find, oh, this is getting tough. The area of a rectangle. Okay, 8 times 4, right? And then, I don't know, what does that turn out to be? 385,728. Actually, it will be in, now think about it, it's a force. You've usually got two choices for force, either pounds or newtons. Fake newtons. Newtons, right? We're in the metric system. Now, why does it make sense that it's in newtons? What was the 12,054 in? Newtons per square meter. What did you just multiply by when you multiplied by 8 times 4? That was 32 square meters. So the square meters canceled, and you're left with the units of newtons. So it's important to realize when you're in the metric system of measurement here that PA stands for newtons per square meter, and then you can remember just by using a little unit analysis what the force units should be. So 385,728 newtons. Okay, so always the force will either be in pounds or newtons, or maybe some multiple of those. Okay. Does that make sense? Any questions there? So did you notice we haven't used calculus yet? All right, so part C, we're going to use some calculus. It says find the hydrostatic force on the end that is 4 meters wide. So guys, this picture that I've drawn, this is the bottom of the tank. So the bottom of the tank, it's 8 by 4. What's the height of the tank that you don't see when you're looking straight down? 1.5. So what's the rectangle I should draw when I'm looking at the force on an end of the tank for part C? Yeah, well, yeah, 4 by 1.5, sure. Now this rectangle doesn't look much different than the other rectangle, but I'm going to say that this length is 4 and this length is 1.5. And that's, again, in meters. So this is the side of the tank. I should actually erase that because I'm going to have to draw something in there, but that's the side. So we want to find the force on the side of the tank, but the problem is the depth of the water is not constant on the side like it is on the bottom, right? So this is where the calculus is going to come into play. We're going to find the force on, what do you think we're going to find the force on? One little representative slice of the side of the tank? One little representative rectangle? So you have to imagine that's a rectangle. It doesn't look much like one. So we'll find the force. In fact, we'll let F sub I represent the force on the ith rectangle. Let's say rectangular piece of the side, I guess. Side of the tank. Does that make sense? So, I mean, on that rectangle, the force will be almost constant is the point. So, I guess we could break it up like this. The formula for force is WdA, right? So W sub I, D sub I, F sub I would be W sub I, D sub I, A sub I. If you want to coordinatize this, you can. This example, it's not so important, but I think it makes sense to put the origin there at the left-hand corner and make the bottom of the tank correspond with the bottom of the tank correspond with the x-axis, I guess, so xy. In other problems, as you'll see, it's going to be really important to coordinatize, but here it won't be as important. Okay, what are we going to call the height of this ice slice? The height we could call y sub I. No big surprise there, right? All right, so what is the weight density then? The weight density of the ice slice W sub I is still going to be 820 times 9.8, isn't it? Okay, what's the depth of the ice slice? So in the picture, what would the depth of the ice slice be? From the top down to the ice slice, I guess. What would that be? 1.5 minus y sub I would be d sub I, wouldn't it? Okay. So 1.5 minus y sub I. Good. And then what's left? A sub I. It's a rectangle, guys. It doesn't have any, it's just a flat object because we're looking at the side of the tank. There's no depth into this screen there, okay? So we're just looking at area. So what's the area of that rectangle? Okay, length times width, but what's the length? So the length, yeah, definitely 4. That's a good start. Times. Yeah, I didn't put it in here, but delta y would be this little thickness right there, right? Delta y. So there's your F sub I. Any questions there? Okay, so what was 820 times 9.8 times the 4? I don't know. Okay, that's what I have. So I get 32,144 for 820 times 9.8 times 4? Okay. And then just throwing in the other stuff, 1.5 minus y sub I, and then delta y. Okay, let's set up the integral that gives us the entire force on that side of the tank. So what could I pull out in front of the integral? 32,144. And then what are we going to integrate from? What's the region corresponds with what?
0 to 1.5.
And we're integrating over that entire region given by the side of the tank, and we're doing it vertically, right? So it goes from, on the interval, from 0 to a height of 1.5. So 0 to 1.5. And then what goes inside as an integrand? 1.5 minus y. And then dy. Which is not the hardest integral you've evaluated this semester, so I'm just going to give you the answer. But you're going to have to tell me the units. So this force then is should be equal to 36,162. What units? Now just use common sense. It's a force. So how do we measure force? Either two ways. Either in pounds or in newtons. Okay? So in this example, an upright plate is dunked in water as shown. So the thickness of the plate is going into the screen is inconsequential here. Okay? We're just interested in the force on the side of the plate. It says find that hydrostatic force on the side of the plate. And it's water, so we're going to use 62.5 for the weight density of water. It changes if it's salt water or if it's some other liquid like milk or gasoline. But for just regular water, assume 62.5. So we have a triangular shaped object, and of course we're going to want to, just like before, just like in the last example, find the force on the ith rectangular piece of that triangle. Okay, let me make a new copy here so I don't mess up the original picture too awful much. Okay. Now, if I enlarge this guy and coordinatize it, I think that's going to help us a lot. And you know, the book might do it differently than I do. Different books do it differently. But I like the way I do it, so I'm not going to change. I'm going to coordinatize it like so. I'm going to put the y-axis corresponding with this vertical side. So here's your y-axis. So where does it make sense to put the origin along this vertical axis, y? Well, I mean, some could argue up here, but I would argue here, which means my x-axis would go through like this. So why? You guys tell me, why am I setting it up that way? Well, yeah, okay, we're going to need the equation of that hypotenuse line segment to find the width of a representative rectangle, because the width of that representative rectangle changes depending on where you place it, right? And we're going to, in order to find the area of that representative rectangle, we're going to need to know that width. So we're going to need to know the equation of that line. And what's easier to find than the equation of a line whose y-intercept is at the origin, right? That's the logic there. So let's go ahead, since we know we're going to need the width of this representative rectangle, let's go ahead and find the equation of this line. Well, in order to find the equation of a line, you need a couple of points on it. I mean, obviously, we set it up so that it goes through 0, 0. You need a couple of points or a point and a slope. What would be the other point that we could get pretty easily based on the given dimensions here? In other words, what are the coordinates of this point?
4, 3.
Yeah, over 4, up 3. Okay. So using just y, since the line goes through the origin, just use y equals mx plus b. What is y equal? So what equation is that going to be? Y equals, and what's the slope? Rise over run, right? So go up 4, up 4 and over 3. So 4/3. Oh no, I'm sorry, I read it wrong. Up 3 and over 4. So 3/4. X plus b, but what's b? 0. Now we can't write it this way, right? Because this is y as a function of x, but when using horizontal rectangles, you guys know we need x as a function of y. So we solve this for x, and we get x equals 4/3 y. Okay. So at some point you have to find that. Now let's then find our f sub I. So then based on this picture and on this representative rectangular piece of the side of that triangular object, let's find f sub I, which we know is weight density times depth times area, right? So fill it in. What's the weight density? Yeah, so just 62.5. That's all we need to put in. Okay, let's go back to the picture for a second. What's the depth of this ith slice? If this height, what would you call the height of the ith slice? Maybe y sub I? So what would the depth be? What would d sub I equal? Yeah, the water line, do you notice that the water line is at a height of 4? So 4 minus y sub I? That's a little tricky, isn't it? Okay, so depth is 4 minus y sub I. And so there's your w times d. W sub I times d sub I. Now the area, a sub I, is referring to the area of the ith slice. Well, okay, width-wise, going from left to right, what's going to give us that width of the ith slice? Exactly that guy, right? So how about 4/3 y sub I times, what's that short height of that rectangle? So this height right here is delta y. Okay? So critical, you can find f sub I, and then the integral's the easier part. So then the total force is going to be what? What could I pull out in front? What should I multiply first? Yeah, what's 4? So it'll be something over 3. What's 62.5 times 4? So 250 thirds. I'll pull outside the integral. Does everybody see where that came from? That's the same as 62.5 times 4/3. And then what are we going to integrate from? Go back and look at the picture. Just look at the region which corresponds to the triangle. That's what you integrate over. And what does that go from in my units? From a height of 0 to a height of 3. And then what would go inside? 4 minus just y, right? Times, oh, careful, there's this little guy hiding right here. Y sub I becomes just y, right? So inside 4 minus y times that quantity times y, and then dy. Again, another easy enough integral to evaluate. Multiply out that y, get 4y minus y squared, find the antiderivative, and apply the fundamental theorem. Don't forget to multiply by 250 over 3. And let me just give you the answer. Approximately, this is equal to, I'm looking at the wrong thing. This is exactly equal actually to 750, but you guys tell me, 750 what? Pounds. It's got to be a force unit, right? So you think English units? Oh, it's in pounds. You think if it's in metric units, oh, newtons. Any questions on that? All right, what else? So I'm not going to do this whole example because it's too much like the other one. But I will fill it in and you can look at it in the notes. To make your life easy, how would you coordinatize it? Where would you put the origin, in other words? That's what you have to think to yourself. Right in the middle? Yeah, maybe. That would work. I would put it on the base, right in the middle on the base. The bottom base, right? Because I suppose trapezoids, isosceles trapezoids have two bases. So I would coordinatize it like so. But then if you do that, okay, you're going to draw your let me make this even bigger. You're going to draw that representative rectangle. I want to see you guys do that. And, finding the depth is going to be very similar. Don't forget it's 1 foot higher than the height of the trapezoid. Finding the depth is easy enough. The weight density is still 62.5. So all that stuff's the same. There's a slight difference in finding the area of this thing, so that's why I wanted to draw it for you. The area, okay, you could find the equation of this line, right? But when you find then the equation of this line and make it y equals whatever, right? Solve it. You get it. You get it y equals whatever, and then you solve it for x, get x equals whatever. That x length is only going to give you half that width of that rectangle, right? So what do you have to do if you want to find the area of that representative rectangle? What do you have to do with that x, that formula x in terms of y? The right-hand part of that formula, what do you have to multiply by? 2, which is different than the last problem. Okay, so you have to be good at drawing these pictures to get the right areas here. Does that make sense to you? So that's the only difference here. That's what I wanted to point out. I didn't want to go through an entire example that looked just like the last one except for that one bit. Does that make sense? Okay. So then the one I do want to work for you is part C. It says a tank has ends in the shape of the region between y equals x squared divided by 2 and y equals 12 measured in feet. Find the hydrostatic force on one end of the tank if it is filled to a depth of 8 feet with gasoline, and then I give you the weight density of gasoline is 42.0 pounds per cubic foot. So it's important. If it's a different fluid, it's important to know what that weight density is. So, okay, this is a little different. Let's graph this thing. Let's graph, so this is the parabola. This is like calculator notation. This is the parabola y equals x squared over 2, or 1/2 x squared. So I think it makes sense maybe to plug in 2. We just want to graph that parabola. That's going to be the shape of the end of the tank, right? So I know it goes through 0, 0. If I plug in like 2 for x, what do I get for y? Like 2 for y? Because 2 squared is 4 divided by 2. Yeah. And same if I plug in negative 2. So the point 2, 2 and negative 2, 2 will be on the graph. And then I don't think I'm going to need to draw the whole thing. In fact, I might even be able to get away without drawing the intersection point of where we have to cut off the height of this tank at. So just draw parabola, and then we're going to cut it off. Let's see, where is it? Let's see, it goes to a height of 12, but I don't even think I care about that because it's only filled to a depth of 8 feet. So I think I want to cut it off for the sake of argument. Let's say this is at a height of 8. Okay, that's where I'm going to cut it off. And then let's see if I don't even know if I'm going to need these intersection points. So let me just draw my representative rectangle, like so. Realize the graph in green here is just y equals x squared divided by 2. And as usual, I'm going to need x in terms of y, because I'm dealing with horizontal representative rectangles here. So if y equals x squared divided by 2, can you tell me what x would equal? In other words, this value would be an x value from the y-axis on out to the edge of the representative rectangle would be an x value. Can you tell me what formula would give me that? So I'd multiply both sides by 2, take the square root, positive square root, what would I get? X equals square root of 2y. Does everybody see that? And so if the height of this thing, if the height of this representative rectangle is, say, y sub I, then the width, at least of half of it, I guess, is going to be square root of 2 y sub I. Okay. Does that make sense? All right, so let's set up f sub I. F sub I. Remember, WDA. W sub I, D sub I, A sub I. What am I going to plug in for weight density? W is weight density of the fluid. So again, what we're trying to find is the force on that side of the tank. So what color is gasoline? It's kind of a little, it's not clear, it's a little off clear, right? Yeah, it is. We'll do brown here. It's really old gasoline. So, yeah, this is crude oil. So that's the side of the tank, right? That I kind of highlighted there. Okay. We're trying to find the total force on the side of the tank. And then, of course, when you're designing a tank, you make sure that it's rated to withstand, or hopefully withstand by a long ways, whatever force is going to be exerted on it. Anyway, so what's the W sub I going to be? 42. That's given as 42. And the depth, if this is at a height of y sub I, what's the depth? D sub I? 8 minus y sub I. Okay, 8 minus y sub I. And then A sub I, the area of that ice slice, of that rectangular slice in red, is going to be what? Well, okay, what's the length again? So we know that this width right here is given by square root of 2y, or y sub I, if you like. So it's going to involve the square root of 2 y sub I, but what do you have to do to it? Multiply by 2, double it. And then that's just the length of the rectangle, the horizontal length of the rectangle in red. So how do you get the height? That little height is what? Delta y. Okay, so that's f sub I. Now, if we go ahead and multiply the 42 and the 2, what can we pull out? So for the force integral, the total force, what can we go ahead and pull out? 42 times 2 is 84. But we could also split up radical 2 y sub I, right? And make the radical 2 outside. Integral, what are we integrating from? Height-wise. Think height-wise. This side of this tank ranges height-wise from 0 to 8. And then what goes inside? 8 minus y. What else? Square root of just y, because I pulled out the square root of 2 part of that. And then what else? dy. Okay? This is easy enough to evaluate. Just remember, the square root of y is y to the 1/2 power. Distribute it. And let me give you the answer. Turns out to be 5,734.4. What units? What units would we be in? Pounds. It's force, right? Total force on the side of the tank.